Before we get into the details of the XADC macrocells, I want you to know that there's a user guide from Xilinx specially for this XADC. And it just, as the title says, that XADC is actually dual, it's 12 bits, and it can sample up to 1 megasamples per second. And the details, there's a ton of details and ton of configurations for this XADC, so I highly recommend that you actually at least take a look at the user guide. Anyway, I'll go through some of the details myself, and at least I'll give you an overview of this macro cell. So in here, you'll see a very simplified block diagram of these XADC. And what it does, it shows us the major components of this macro cells. And really, the main components are actually these dual ADC. So it's called dual ADC because it has two ADCs. Each one of these ADCs is exactly 12 bits. They do sample 1 megasamples per second, or MSPS. And they do operate on differential input. What does it mean by differential input is that each one of the channels that actually can sample has to have a negative and a positive. It doesn't have to be negative and positive. For example, as it turns out that there are a couple of modes that it operates at, which are unipolar, and it goes from 0 all the way to 1 volt, or bipolar from -5 to 5 volts. We will be using the unipolar to construct our XADC core. And as you can see from these modes of operations, as it turns out that the maximum swing for the input is up to 1 volt. So that it can, between the two ports of the ADC for each channel, it can only read up to basically 1 volt. Okay, so what else? So these are the main components. The other components, as it turns out, that the XADC also has on-chip sensors, and the on-chip sensors measure the different voltages and the temperature, because the FPGAs has very strict operational constraints on the power supplies and whatnot. So you need to monitor them. So it has, for example, what's the temperature of the FPGA, what's the core voltage and whatnot. We will be monitoring these, or at least a couple of them. Specifically, we'll monitor the die temperature and the core voltage, so we can actually take some actions or set some alarms for our subsystem if we wanted to, for our prototyping system. In addition, there are analog multiplexers, because as it turns out that we can, not only can we actually measure the on-chip temperature and voltages, we can actually digitize external signals. And because we only have a couple of ADCs in here, what we need is some sort of way to read all of them in some sort of a sequencing. So what we will be using, or what the XADC provides us with is our analog multiplexers. These are not normal multiplexers that we see, they're analog, meaning they actually route analog signals to analog outputs, okay? But they're controlled, or they serve similar purpose as the muxes or the multiplexers we built before. So these are extremely useful because we can actually support many channels using only a couple of ADCs. For example, if we want to use just this ADC, we can just use that ADC and we can sample so many external signals. If this ADC is operational, for example, at a 1 megasample per second, and we want to do 4 channels, or we want to sample 4 channels, it will appear as if that we have 4 different ADCs, and each one of them is a quarter of a megasample per second. Meaning it will appear that there are 4 slower ADC, even though that we only have 1 ADC. And the way we do it is by utilizing this multiplexer. So we route one signal, we sample it, and then in the next round we route the second sample and we sample it, or the next signal and we sample it, and so forth, and 4 of them. And this is what we call a sequencer mode. Okay, this is at least how Xilinx actually calls it. It calls it sequencer mode. You can think about it, it's a round robin fashion, basically, one at a time. And it will appear from our perspective, from our system perspective, it will appear that as if we have 4 different ADCs, even though physically we only have one faster ADC. Okay, so the 2 ADCs, we have analog multiplexers so that we can actually route different analog signals, including some on-chip temperatures and voltages. Next, we have a control and status register, and as it turns out that this is just a bunch of registers. That's as the name implies, it's just registers. And how many of them exactly? Well, we have a total of 128. So because we have a total of 128, this is equals to 2 to the 7. That means I need 7 bits for the address. This is important, and we're going to utilize it in the wrapping circuits later. Anyway, so these control and status registers, if you really take a look at them, they're split in half. Each one of them is actually 64 rows, and each word within these registers is actually 16 bits. Some of them are control registers, other are status registers. So control registers actually sets up the different aspects of the ADC, the analog multiplexers, which of the channels you want to actually do, and so forth. It actually sets a lot of control. So if you want to control these ADCs or change them, you need to change these control registers. The status registers, on the other hand, they actually contain the actual physical digital numbers that you can that the ADC outputs. So whenever it outputs, or okay, I measured the on-chip temperature, it actually stores it in one of the registers in here. Okay, and there are many of them, and there's actually a register map that you can check on the within the user guide for the XADC, and you can see it. And of course, there are different status as well. So the last part, which is the dynamic reconfiguration port interface, its purpose is actually to serve as a way to interface with these control registers, and it operates like an I/O, any normal I/O. Like basically a mapped I/O, a memory mapped I/O. Basically, you can specify an address and get access to it and whatnot. So it's extremely useful, and it's called a dynamic reconfiguration because, as it turns out, that if you actually put some sort of an optional circuit in here, you can change the control registers. And if you change the control registers, you're controlling how, or you're changing how that XADC actually functions. So you can dynamically reconfigure these ADC to do different things. Okay. For our purposes, we're gonna just set them once and just leave them and utilize them as normal ADCs that digitize several signals. Okay, so we have many signals in here, and as it turns out, the XADC can support up to 17 channels. One of these channels can be completely dedicated analog channel, basically at the fastest speed, which is 1 megasample per second, and we can have up to 16 auxiliary analog channels. You don't have to utilize all these, but if you did, if you do, you can actually have all these 16. Okay. The one you do not use as analog are actually utilized as digital I/O pins, similar to how microcontrollers actually deal with ADC cores or ADC I/O modules. Of course, the other channels that we can implement actually internal temperature and voltage sensor readings as well, the different voltage reading, and we can actually just map it inside it. So we can have up to 17 external analog channels dedicated passed into the XADC, and we can also have the internal temperatures and the voltages from the different sensors. So what are we going to utilize in our specific implementation of the XADC? Well, we're going to utilize only 4 auxiliary channels. So we on this particular JXADC, the PMOD, we will only have 4 different external analog inputs to the system. And the reason why we only have 4 is because you need to physically route it from the FPGA chip all the way to the outside world, and the Nexus board that we're using only maps 4 of them. The other 2 signals are internal signals. We're going to see the die temperature, and according to the datasheet and according to the user guide, actually the temperature can go from negative 273 Celsius all the way to 230 Celsius. The core voltages, even though the FPGA actually operates at 3.3 voltage, according to the datasheet and the user guide, actually it goes from 0 to 3 volts. This is how it actually measures it.